Welcome! In this video, we'll be tackling problem number 2164, sort even and odd indices independently. This problem is an excellent opportunity to explore array manipulation and sorting techniques by separating even and odd indices. Stick around as we dive into the approaches to solve this step by step. In this problem, you're given a zero-indexed integer array called nums, and your task is to sort the values at even and odd indices independently. Specifically, you need to follow three steps. First, sort the values at the even indices in non-decreasing order, which means arranging them from smallest to largest. Next, sort the values at the odd indices in non-increasing order, which means arranging them from largest to smallest. Finally, merge these sorted values back into their original positions in the array so that the even-indexed values remain at even indices and the odd-indexed values remain at odd indices. The goal is to return the updated array after applying this sorting process. Let's look at some examples to make the problem clearer. In the first example, the input array is nums equals 4, 1, 2, 3. The values at the even indices, 4, 2, are sorted in non-decreasing order to become 2, 4. Meanwhile, the values at the odd indices, 1, 3, are sorted in non-increasing order to become 3, 1. When we merge these sorted groups back into their original positions, the result is 2, 3, 4, 1. In the second example, nums equals 2, 1, the even indices contain 2, and the odd indices contain 1. Since there's only one value in each group, no sorting is needed, so the output remains 2, 1. In the third example, nums equals 7, 8, 1, 6, 5, 4, the even indices contain 7, 1, 5, which are sorted to 1, 5, 7 in non-decreasing order. The odd indices contain 8, 6, 4, which are sorted to 8, 6, 4 in non-increasing order. After merging, the result is 1, 8, 5, 6, 7, 4. Now let's consider the constraints and some edge cases. The length of the array, nums.length, is between 1 and 100, and each element in the array lies between 1 and 100. For edge cases, if the array contains only one element, such as nums equals 5, the output is simply the input because there are no odd indices to sort. If all elements fall under either even or odd indices, like in the case of nums equals 2, 4, 6, the sorting is applied only to the respective group of indices. Additionally, duplicate values are managed naturally by the sorting process, so you don't need to handle them separately. These constraints and edge cases help ensure the problem is well-defined and manageable. To solve this problem, one straightforward approach is the brute force method. Here, the idea is to first separate the values at even indices and those at odd indices into two distinct lists. Once we have these lists, we can sort the even-indexed values in ascending order and the odd-indexed values in descending order. Finally, we reconstruct the array by placing the sorted values back into their respective positions in the original array. While this approach is simple to understand, it has certain trade-offs. The time complexity is dominated by sorting the two lists, which adds up to O n asterisk log n. Additionally, it requires extra space to store the two separate lists, making the space complexity O n. While the logic is clear, this method involves multiple traversals of the array and extra memory usage, which can be less efficient for larger inputs. To address the limitations of the brute force approach, we can optimize the solution by avoiding the creation of auxiliary lists. Instead, we can sort the values at even and odd indices directly within the original array. This is achieved by identifying the even and odd indices, and then sorting the corresponding values in place. Specifically, the even-indexed elements are sorted in ascending order, while the odd-indexed elements are sorted in descending order. This reduces the additional space usage, as we no longer need to store separate lists. The time complexity remains O n asterisk log n due to the sorting operations, but the space complexity can be reduced to O(1) if sorting is done in place. However, this optimization comes with its own challenges, as implementing in-place sorting with different orderings can make the code more complex and harder to maintain. For this problem, the chosen strategy strikes a balance between simplicity and efficiency by combining the benefits of both approaches. We use auxiliary lists to handle even and odd indices separately, which simplifies the implementation while avoiding the complexities of in-place sorting. The main insight here is that sorting even and odd indices independently allows us to treat them as two smaller subproblems, making the solution modular and easier to implement. The process involves splitting the array into two lists based on index parity, sorting the even indexed values in ascending order and the odd indexed values in descending order, and then reconstructing the array by filling in values from these sorted lists. This approach avoids the pitfalls of in-place sorting while still being efficient. The chosen approach offers a practical trade-off between simplicity and performance. By using auxiliary lists, the implementation becomes more straightforward and less error-prone compared to in-place sorting. This ensures that we maintain the desired time complexity of O(n*log n, while keeping the memory trade-off minimal for most practical input sizes. The separation of sorting and merging logic makes the code more intuitive and easier to debug, even though it uses slightly more memory. Overall, this strategy is simple to implement, efficient, and avoids unnecessary complexity, making it the ideal choice for solving the problem. To solve this problem, we start by understanding the setup. We are given an array of integers, and our goal is to sort the elements at even indices in ascending order, while sorting the elements at odd indices in descending order. The positions of the indices in the array should remain unchanged, but the values should be replaced with their respective sorted counterparts. The first step in our approach is to separate the values based on their indices. As we traverse the array, we identify each index as either even or odd. For even indices, we append the corresponding values to a list called even_values, and for odd indices, we append them to a list called odd_values. This separation is critical because it allows us to focus on sorting each group independently without mixing their values. For example, if the input array is 4, 1, 2, 3, 6, 5, the even indices give us the values 4, 2, 6, and the odd indices give us 1, 3, 5. By splitting the array this way, we simplify the sorting process significantly. After separating the values, the next step is to sort the two lists. The even_values list is sorted in ascending order, while the odd_values list is sorted in descending order. For instance, using the previous example, the even_values list, 4, 2, 6, becomes 2, 4, 6, after sorting in ascending order, and the odd_values list, 1, 3, 5, becomes 5, 3, 1, after sorting in descending order. Once the values are sorted, we move on to reconstructing the original array. Here, we use two pointers, even_ptr and odd_ptr, both initialized to 0. As we iterate through the array again, we check each index. If the index is even, we replace the current value with the next value from even_values using even_ptr, and then increment the pointer. If the index is odd, we do the same using odd_values and odd_ptr. This method ensures that the sorted values are placed back into their respective positions without overlap. For example, after reconstruction, the array 4, 1, 2, 3, 6, 5 becomes 2, 5, 4, 3, 6, 1. The last step of the algorithm is to output the reconstructed array as the final result. In our example, the final output is 2, 5, 4, 3, 6, 1. The process of separating, sorting, and reconstructing the array highlights two important insights. First, by sorting the indices independently, we simplify the problem into modular steps that are easier to handle. This index-based sorting ensures clarity and avoids unnecessary complexity. Second, the efficiency of the algorithm is notable. Separating the array into two lists takes O(n) time, sorting each list requires O(n)log n in total, and reconstructing the array takes another O(n). Therefore, the overall time complexity is O(n)log n, making this approach both effective and efficient for the problem. In terms of space complexity, the algorithm uses two additional lists, even_values and odd_values, which store the separated values from the input array. Since these lists collectively require O(n) space, the space complexity of the algorithm is O(n). Let's also consider the data structures involved. The input array ARR serves as both the source of data and the container for the reconstructed result, allowing us to perform in-place updates. The auxiliary lists even_values and odd_values provide temporary storage for the separated values, enabling efficient sorting. Finally, the pointers even_PTR and odd_PTR are simple integer counters that help track positions during reconstruction. This combination of data structures ensures the algorithm remains straightforward and easy to implement. The algorithm also handles a variety of edge cases gracefully. For an empty array, the algorithm simply returns an empty array, as there are no values to process. If the array contains a single element, no sorting is needed, and the array is returned as is. In cases where all indices are either even or odd, the algorithm works naturally, as one of the lists will be empty, and reconstruction proceeds without errors. Finally, when the array contains duplicate values, the sorting step preserves the stability of the original order within each parity group, ensuring that the result is both correct and consistent. These considerations make the algorithm robust and capable of handling diverse scenarios effectively. The provided solution efficiently solves the problem of sorting even and odd indexed elements independently. Here's a step-by-step explanation. 1. Extract even and odd indexed elements. The list comprehension, nums, I, for I in range, len, nums, if I%2 equals 0, gathers all elements at even indices into the even_indices list. Similarly, nums, I, for I in range, len, nums, if I%2 is not equal to 0, collects all elements at odd indices into the odd_indices list. 2. Sort the extracted lists. The even_indices list is sorted in ascending order using sort. The odd_indices list is sorted in descending order using sort, reverse equals true. 3. Reconstruct the result. An empty list result is initialized to store the final output. Two pointers, even_idx and odd_idx, are used to track the current position in the sorted even_indices and odd_indices lists, respectively. A for loop iterates over the indices of the original array. If the current index is even, the next smallest value from even_indices is appended to result. Otherwise, the next largest value from odd_indices is appended. 4. Return the final result. After the loop completes, result contains the original array with even indices sorted in ascending order and odd indices sorted in descending order, as required. This approach ensures that the sorting is done efficiently, with a time complexity of approximately O(n) log n, where n is the length of the input array. The space complexity is O(n), due to the additional lists used for even and odd indexed elements. Here, we start by importing necessary Java utilities like java.util** to make use of collections for sorting. Inside the sort_even_odd method, the goal is to sort elements at even and odd indices independently. We first create two lists, even indices to store elements at even indices and odd indices for elements at odd indices. Using a for loop, we iterate through the input array nums. For each index, if the index is even, we add the element to the even indices list, and if it's odd, we add the element to the odd indices list. This separates the array into two distinct groups based on their indices. Next, we sort the even indices list in ascending order using collections.sort. For the odd indices list, we use collections.reverseOrder to sort it in descending order. Once the two lists are sorted, we need to merge them back into the original array while maintaining their respective positions. To do this, we initialize two pointers, even_idx and odd_idx, both starting at 0. In the second loop, we iterate through the array nums again. If the current index is even, we take the next value from even indices and assign it to the current position in the array, incrementing the even_idx pointer afterward. If the current index is odd, we take the next value from odd indices and place it back into the array, incrementing the odd_idx pointer. This ensures that the elements from the sorted lists are placed back into their correct positions based on the original index parity. Once the loop finishes, the nums array has been fully reconstructed, with even indexed elements now sorted in ascending order and odd indexed elements sorted in descending order. Finally, we return the modified array as the result. This approach ensures that the sorting is done efficiently and maintains the original structure of alternating indices while meeting the problem's requirements. To solve the problem, we start by separating the elements of the array based on their indices. The elements at even indices are 4 and 2, so we store them in the even_indices list as 4, 2. Similarly, the elements at odd indices are 1 and 3, which go into the odd underscore indices list as 1, 3. Next, we sort these two lists independently. The even underscore indices list is sorted in ascending order, resulting in 2, 4, while the odd underscore indices list is sorted in descending order, giving us 3, 1. Finally, we merge the sorted values back into their original positions. Starting with an empty result list, we iterate through the original array. At each even index, we append the next value from even underscore indices, and at each odd index, we append the next value from odd underscore indices. This process results in the final array 2, 3, 4, 1. Now, let's look at another example where nums is 2, 3, 1, 5, 4. First, we separate the even and odd indexed elements. The numbers at even indices are 2, 1, and 4, which form the even underscore indices list as 2, 1, 4. For the odd indices, the numbers are 3 and 5, resulting in the odd underscore indices list 3, 5. After separating, we sort the even underscore indices list in ascending order, giving us 1, 2, 4, and sort the odd underscore indices list in descending order, resulting in 5, 3. These sorted lists will now be merged back into their original positions to reconstruct the final array. To merge the sorted lists into their original positions, we initialize an empty result list in two pointers, even underscore idx and odd underscore idx, both set to 0. As we iterate through the nums array, we append values from the even underscore indices list for even indices and from the odd underscore indices list for odd indices. For index 0, which is even, we append 1 from even underscore indices, updating the result to 1. At index 1, which is odd, we append 5 from odd underscore indices, making the result 1, 5. Continuing this process, we append 2 at index 2, 3 at index 3, and finally 4 at index 4. This gives us the merged result 1, 5, 2, 3, 4, which is the final output for this example. In this next example, nums is 7, 8, 6, 5, 4, 3, 2. First, we separate the elements into even and odd indexed lists. The even indices contain 7, 6, 4, and 2, so even underscore indices becomes 7, 6, 4, 2. For the odd indices, the elements are 8, 5, and 3, which make up the odd underscore indices list as 8, 5, 3. After separation, we sort the even underscore indices list in ascending order, resulting in 2, 4, 6, 7, and the odd underscore indices list in descending order, giving us 8, 5, 3. These sorted lists are then ready to be merged back into their respective positions. To merge the sorted lists back, we use the same approach as before. Starting with an empty result list in two pointers, even underscore idx and odd underscore idx, at 0, we iterate through nums. At index 0, we append 2 from even underscore indices, resulting in 2. At index 1, we append 8 from odd underscore indices, making the result 2, 8. For index 2, we append 4, then 5 at index 3, and 6 at index 4. At index 5, we append 3, and finally, at index 6, we append 7. The final merged array is 2, 8, 4, 5, 6, 3, 7, which is the sorted version based on the given rules. To analyze the time complexity of this solution, we can break it down into three main steps. First, we separate the even and odd indexed elements from the input array. This involves iterating through the array twice, once to extract the even indices and once for the odd indices. Since the input array has a size of n, each of these operations takes n time, resulting in a total of n for this step. Next, we sort the even and odd indexed elements. Sorting the even indices, which contain about n/2 elements, requires n/2 log n/2 time. Simplifying this, we get n log n. Sorting the odd indices in descending order involves the same complexity, n log n. Combining both, the sorting step contributes n log n. Finally, we merge the sorted even and odd indexed elements back into their original positions. This requires a single iteration through the array, taking n time. Together, these steps result in a structured breakdown of the time complexity. Now, summing up the contributions from each step, we get n for separating indices, n log n for sorting, and n for merging. Since O, n asterisk log, n, is the largest term, it dominates the overall time complexity, making it O, n asterisk log, n. Shifting to space complexity, let's examine the auxiliary space used. The even and odd index lists each hold approximately n/2 elements. Storing these requires O, n/2 space for each list, which adds up to O, n space overall. Additionally, the result list, which contains all n elements, also requires O, n space. These are the primary contributors to the space complexity so far. Now, let's consider the space usage during the sorting process. Python's built-in sort function, which uses timsort, has a worst-case auxiliary space complexity of O, n. This temporary storage is used separately for sorting the even and odd indexed lists. However, since these lists are disjoint, the total space required for sorting remains O, n. Adding up all the components, the total space complexity of the solution is O, n. Comparing this with a brute force approach, where nested loops would manually compare and sort the elements, the naive method would take O, n squared time. This is significantly worse than the O, n asterisk log, n, achieved here. However, the space complexity for the brute force approach remains O, n, as it also requires auxiliary lists for even and odd indices. The optimized approach leverages efficient sorting algorithms to achieve an O, n asterisk log, n, time complexity, which is optimal for sorting-based solutions. The space complexity remains O, n, due to the use of auxiliary lists. Let's also analyze the best, average, and worst-case scenarios. In the best case, such as when the input is already sorted, the sorting step still dominates, leading to O, n asterisk log, n. For randomly ordered inputs, the average case complexity remains O, n asterisk log, n. Even in the worst case, like when the input is reverse sorted, the sorting step continues to dominate, maintaining the complexity at O, n asterisk log, n. This consistency across all scenarios highlights the efficiency and robustness of the optimized solution. When solving this problem, there are a few common mistakes to watch out for. First, failing to account for edge cases is a frequent issue. For example, your solution should handle scenarios like an empty input array or an array with just one element. Testing with minimal inputs ensures your solution is robust. Another mistake is mixing up even and odd indices with even and odd values. Remember, indices represent positions in the array and are distinct from the values stored at those positions. It's a subtle but critical distinction. Additionally, errors often arise when merging the sorted subarrays back together. Using the wrong indices or not alternating correctly can lead to incorrect results. A good approach is to use 2 pointers, one for each subarray, and carefully alternate between them during reconstruction. Finally, inefficiencies in sorting can sneak in. For instance, sorting both subarrays when the problem only requires one to be sorted in a specific order wastes time. Always aim to optimize your sorting logic based on the requirements. Another important consideration is space complexity. While creating separate lists for even and odd indices can simplify your solution, this approach increases space usage. If the problem explicitly requires in-place operations, such an approach might not be valid, so always pay attention to constraints. Beyond these technical tips, there are useful interview strategies to keep in mind. Recognizing patterns is key. Many problems involve separating, sorting, or processing subsets of an array. Practice breaking problems into smaller, more manageable tasks. It's also crucial to clarify the requirements up front. For example, confirm whether even and odd indices are defined using 0-based or 1-based indexing to avoid any misinterpretation. Interviewers also value solutions with optimal complexity. While brute force might work, finding ways to eliminate redundant operations like avoiding unnecessary sorting and leveraging efficient data structures can set your solution apart. Lastly, modular design is a best practice. Breaking your solution into clear functions for separation, sorting, and merging not only makes it easier to debug but also demonstrates strong coding discipline. This problem shares similarities with several other problems on LeetCode, which can help you deepen your understanding. For instance, LeetCode problem 905, sort array by parity, focuses on separating even and odd values rather than indices. Similarly, LeetCode 75, sort colors, emphasizes sorting while adhering to specific constraints, often requiring efficient in-place techniques. Another related problem is LeetCode 280, wiggle sort, which involves alternating sorting logic, much like the alternating patterns for even and odd indices here. Finally, LeetCode 922, sort array by parity 2, is perhaps the most directly related. It involves separating and merging even and odd indices, making it an excellent practice problem for refining the techniques used in this challenge. Exploring these problems will not only give you more practice but also help you identify common patterns and solutions. There are also alternative approaches you can consider to solve this problem. One option is in-place sorting, where instead of creating separate arrays for even and odd indices, you rearrange elements directly within the original array using two pointers. This approach reduces space complexity to 1, which is beneficial, but it can make the implementation more complex and harder to debug. Another option is to use a custom sorting function with a comparator that organizes elements based on index parity directly. This avoids the need for manual separation but may be less intuitive and requires a strong understanding of sorting algorithms. Finally, if the input constraints allow, you could use counting sort. This is particularly efficient when the values are bounded within a small range. However, this method is only applicable when the problem's constraints permit it. Each of these approaches involves trade-offs, so the best choice depends on the specific requirements and constraints of the problem you're working on. Thank you for watching. Today, we solved a problem that highlights the importance of sorting and array manipulation techniques. Remember to keep practicing these concepts to strengthen your problem-solving skills. Don't forget to like, subscribe, and share for more content. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!